hopefully you'll see this in homework 2 as we put it together. So let me share my my screen with you here real quick. Right hand side here. Okay, so this, by the way, I made one little modification. I felt like this introduction module was getting a little too junky, so I moved the homework assignment down to here, and I apologize. So homework 2 looks like it's posted. Part of it is the other 2 pieces I haven't populated yet, so I'll do that right after class, and I'll send you an email with that. I didn't think that would be shown to you, but there it is. The student view then is sort of what you should see. So here's homework 0, you've already done. Here's homework 1, which is due tomorrow, and then homeworks. There are 3 parts to homework 2, and let me explain why there's 3 parts. The first part is simply going to the Wiley Plus problems. There will be, I think, 8 of those. And then there are 2 problems that will be written. And here's what we want you to do. I'm going to post in each one of these parts 1 problem for you to work on, like to write out, like you've done for the last homework. But each of these, part 2 and part 3, will only be 1 problem a piece. What that's going to allow us to do on the grading side is allow us to split up and have 1 person grade what we'll call part 2 and 1 person grade part 3. And the idea then is that we can be very consistent in grading a single question that each of you will have done to make sure that like Alexi doesn't come up with one interpretation of how it should be graded, and I come up with a different one, and so forth. So there, from going forward, we'll generally have 3 parts to the homework, to each homework assignment. So 1 part will be a set of Wiley Plus problems, and then the other 2 pieces will just be 2 written problems. 1 written problem will be part 2, another written problem will be part 3. So I don't want to completely leave the sort of approach of making sure that you can write things out and so forth, and organize your work in a clear way. And so that's why we're sort of having this hybrid approach. When you're doing a written problem, though, there isn't all that scaffolding resources for you to work with, to use. Okay, so what we'll do moving forward then, one other thing. When we get into grading then, what you'll see is, like right now there are 8 problems in the Wiley Plus component of this homework 2. You'll get a grade 0 through 8. Right, and you also, by the way, I've set it up for you to be able to have as many as 5 attempts for each one of those problems. Only after the 2nd attempt would you start to lose credit and not get full credit for it. I think I put minus 10% on that. So it would go down if you worked beyond a 3rd attempt. But again, you should have these integrated opportunities to have some support for your learning while you're working through that. Elizabeth, I'll get to you in just a second. Let me just go over so everything here in the introduction I've left as it was before. So we've got the notes, the original link to all the notes. We've got the lecture 1 video, that poor printout from the textbook I tried to give you guys, the scan of the 2 ways of purchasing
to get our access code from the bookstore.
So let's work through some problems. Finally then, just a note, homework 1 is posted, that's due tomorrow night. Homework 2, you saw it's partially posted right now. Part 1 is available to you to start working on right away. Part block slides down a smooth inclined surface as shown in this figure. Determine the terminal velocity of the block if the 0.1 millimeter gap between the block and the surface contains SAE 30 oil at 60 degrees Fahrenheit. Assume the velocity distribution in the gap is linear and that the area in the block in contact with the oil is 0.1 square meters. And we assume here that the angle of incline for this ramp is 16 degrees. Okay, so that's that alpha value. All right, so first we're gonna start with just trying to think through how to set this up. Now, for the most part, yes, this block is moving. However, we expect to have, from a force perspective, a static situation in that forces will be opposing each other and they will sum to zero in their direction. So let's first draw a free body diagram to kind of figure out which forces are involved so that we can set up an equation with those and hopefully find a way to solve for velocity. That's the ultimate goal here. All right, so if we start with the free body diagram, my apologies before I show this. I zoomed in a bit on it. It's a little bit rough, but here's our block, okay? It's a rectangle. Of course, it has weight acting vertically down, right? We can't ignore the gravitational constant here, all right? We've been given that it's a 10 kilogram mass, so it won't be hard to figure out that force here. But what we're going to do with respect to working on this problem is V is acting in what we might consider the X direction. So I'm modifying. Now the global, vertical is still set up the same way, but we have a local, right here on the right, you can see sort of this local XY coordinate system. So X is going down the ramp, or parallel to the ramp, and Y is going to be orthogonal or normal to that X direction, so going vertically up or down away from the ramp, right? Now, so we have our weight, that's going to be acting in the downward direction. And then the other force that we have that we talked about the other day is this shear stress force here that's acting in the X direction here, all right? That is where the block is interacting with this oil. And I had some good conversations yesterday with a few folks who were asking about viscosity in my office hours. So let me just try to recreate those for everybody here. The oil, even has a very thin layer. Remember we said at the top of the oil, when we have the block in place, the molecules that are closest to that block, that are in contact with that block, are going to be moving at the velocity v. The molecules that are in contact with the base of this ramp are going to be going zero. And so what we've been told here is assume the velocity distribution in the gap is linear. So we're going to linearly change within that thickness of, the small thickness of oil, from 0 to v, okay? And it's going to be just a proportional increase from 0 to v based on the height above the ramp base. Okay, so the viscosity is really a property that tells us, okay, if you've got your molecules of this fluid in contact with the bottom of the block, how sticky are those? And what we really mean is, how well connected are they to the other molecules within that layer of oil, such that the ones at the surface are going to pull, or the ones that are in contact with the bottom surface of the block, how much are they going to pull and hold on to the ones, the next molecules down, and the next molecules down, and the next molecules down? So remember, we said honey was very viscous, and it doesn't flow that well. So you can think of viscosity as a resistance to movement, a resistance to flowing, okay? And so with that, what we're going to do here is eventually we're going to tau, of course, shear stress. We're going to bring viscosity into that in just a moment, and we're going to use this linear velocity framework to help us out with that. Okay. All right. So let's take this a step further. Now, if we have a constant velocity, so V reaches terminal, or the block reaches terminal velocity V, capital V here, then the sum of the forces equals 0, which is to say that gravity pulling the block down the ramp is in balance with the viscous forces of the fluid that are trying to hold it back, in this case oil, that's on the bottom of the block, between the block and the ramp, right? Okay, so the first one we talked about was the weight of the block acting vertically downward But there's a horizontal component to that, right? Because the ramp is at an angle, there's a horizontal component of W working down, and because it's on the slope. And so, of course, what we're going to do, as you may recall from both statics classes and your fundamental dynamics classes of physics, particle physics, we're going to use W, the weight of the block, times the sine of alpha. Okay, that will give us the component of the weight that is acting in the direction, in the x direction. Then there's a viscous shear force. All right, where does this come from? On the left-hand side, on our free body diagram, we have written here tau times A. And this is our viscous shear. The force turns out to be, the shear stress is tau, and a shear stress is always in terms of force per area, all right? So if we take that shear stress and we multiply it by an area, in this case, it's going to be the contact area between the block and the oil, then tau times A will give us the viscous force that is associated with that shear stress, okay? So the viscous shear force then is tau times A, right? Now, we've included some of the geometry here, right, of the system with our sine alpha for the weight part. We really don't have to do that for tau times A, because that is only working in the direction, this x direction up or down the slope here of the ramp. It's only working in that direction, right? Okay, so I've put our free body diagram on the right-hand side here, and on the left, I've just gone ahead and equated these two forces with each other. So W sine alpha is on the left-hand side, tau times A is on the right-hand side. Those have to be the same magnitude working in opposite directions for this to work out. So let's figure out how to work with or populate this equation. Now the weight part is going to be easy, right? Because it's m times g, right? The mass of our block times the gravitational force, gravitational acceleration, pardon me. And then the right-hand side, and we're given alpha, right? So we can calculate the sine of 16 degrees. On the right-hand side, tau, we need to figure out A is given, and A is just given right here. When we read this, we say assume the velocity distribution in the gap is linear and that the area of the block in contact with the oil is 0.1 square meters. So that is our area of contact between the block and the oil, and that's what will go in for A. All right. I had forgotten, when I was typing this up, I sort of forgot about, they has asked for or noted this velocity distribution will be linear. And so we're going to assume, we can assume it because it was given as well, that we have a linear velocity distribution. I'm going this over, oops, that, this, move it over. Okay. Let's see. Okay. Okay, so there's a question, what's the difference between the viscous shear stress and the viscous shear force? The shear stress is tau, and that is always in force per area. So a shear stress is always in force per area. The shear force that's associated with that is just tau times A. All right, so on the right-hand side of our equation right here, tau times A gives us a force. Tau by itself would be force per area, okay? All right, so, oh, shoot, gotta do that. Okay, so tau, if we go back to the definition that was in the book, we said that shear stress that's associated with this viscosity is equal to our dynamic viscosity mu multiplied by du dy, or the velocity gradient vertically in that thin layer of oil, all right? And so this is where we put a little bit of know-how together. The other relationship, remember, that we talked about in our in the book, we sort of said, well, there's also this way of saying U over B. Well, where does that come from? What that allows, essentially, that says that we can put in the velocity. Remember, we're going from 0 to v over that thickness, 0 to 0.1 millimeter here, right? And so the du dy can be approximated by going from 0 to v. So if we were going to integrate this, it would be v minus 0, so that would go away, and it would just be v velocity in the numerator. And then in the denominator, we would go from 0.1 millimeter to 0. So if we subtract the 0 off, we basically end up with v over the thickness b, we might call that. Okay, so du dy is approximated by just saying what is the velocity at the top, because the velocity at the bottom has to be 0, and what is the thickness over which that velocity is changing. So we simplify this with v over b. In this case, v is we used u over here to indicate a general velocity. In this case, we've replaced it with v because v is the terminal velocity of this block. We could have called it, I don't know, little v or whatever, but I just want you to know that we were explicit about that. B is simply representing the thickness. So this du dy is being represented by two constants that we have in our problem here. Okay, so now we can substitute into the force balance equation. Here's our force balance equation to try to work this out. So we say that W, the weight of our block, sorry, the font changed because I went into the equation mode in PowerPoint, but weight times the sine of alpha is equal to tau times A, so that's what we have over here. And then on the right-hand side now, we're going to replace tau with this mu, the dynamic viscosity, times the velocity at terminal velocity v over b, all right? But we can't forget the a. Remember that the a is included at the right-hand side there, right? So now we've got something we can work with, and more importantly, we have v represented in there, right? So we could rearrange this and solve for v, and the only thing that we've done up to this point is really said that these two forces are opposite of each other. They have the same magnitude, and therefore we can re-represent those forces in this way, which includes v, so that we can solve for it. All right. So if we rearrange this equation and solve for v, then we have w times the sine of alpha. Over here, we multiply by b, so b comes up there. We divide by a, and we divide by mu, right? And so this should stand. This should work for us. And we can now take this a step further to re-represent w, the weight force, as m times g, right? M, the mass of this, this block, and g, the gravitational acceleration. I was trying to get the equation editor hung up a little bit. I tried to put these parentheses around to get this to look like this sign, but anyway, I apologize for that. But sine alpha is what we needed in that side. So all we've done is replace w with sine g there, and now take this a step further. One of the things that, of course, we need here is mu, right? That's in the denominator there. And we've been given that the oil is SAE 30 at 60 degrees Fahrenheit. So this is where you want to turn to the tables that I uploaded in the first part. They'll also be in the Wiley Plus content. For now, though, if you're just working with the PDFs of the information that I posted, you've got these tables on the inside cover. One of them is, one set is for liquids and one set is for gases, but you should be able to look at this and basically within each of those sets, one is the British units and one is SI. So if we go to SI, we see SAE 30 oil with a temperature of about 56 degrees Celsius, which is pretty close to 60 degrees Fahrenheit. We look over and the dynamic viscosity comes out to be 0.38 Newton seconds per meter squared. Okay, so we can look that up, and that's going to get help inform our equation. All right, so now I'm going to take that equation from the previous slide, So we had made this step on the previous slide. Now let's start populating this. So B, recall, was 0.1 millimeter. So that's there. I put in a conversion to turn millimeters into meters. And the reason I did that is that I knew I was going to have meters over here for our gravitational acceleration. So I'm converting to meters right there. Then I have m, our mass, 10 kilograms, g, the acceleration due to gravity, 9.81 meters per second squared, and then the sine of 16 degrees. Then we divide by, now we've got mu, so 0.38 Newton seconds per meter squared, and then A was 0.1 meters squared, all right, which was given right here again. So now we can work our way through this, and if I did my math right, this should come out to 0.071 meters per second, right? So pretty slow, you know, not moving very fast, obviously. What would it take? Let's see, so that's, I guess that is 7 centimeters per second. So what is that? You know, almost 3 inches, something like that, you know, 2.5, somewhere in there. So, you know, not unreasonably fast, not unreasonably slow. One good gut check maybe is to just say, well, does that make sense? And in a relative sense, it makes sense in that it's not 7,000 meters per second, right? Like that would seem a bit too fast. But it's also not necessarily the snail's pace of, you know, 0.07 millimeters per second, right? That would be 1,000 times slower. So, you know, just try to think a little bit about whether these seem reasonable to you as you work through them. All right. I hope that helps you for the last problem on the homework, but also just provides a little bit of an overview with respect to how we can use the viscosity relationships, the shear stress that we learned with viscosity to try to include into these types of problems. I guess real quick, what I'd like to do next is shift back to wrapping up surface tension in a little more detail than we did on Tuesday. So before I do that, are there any questions on this before I move on? You can either type them into the chat or unmute or raise your hand.
Just to go back, you converted the B value to meters. Is that just because you want it to be velocity in SI units, or is there something else that like stuck out to you? I didn't hear that part.
Oh, the thing that stuck out. Good question, Grady. The thing that stuck out was this was given in millimeters, right? Our B was in millimeters, and I knew I was going to have meters per second squared for my acceleration due to gravity. So I just needed to make sure I was in the same units. That's all.
Okay, thank you.
You bet.
Yeah, I have one more question about units too. Where does the kilograms cancel? Because it's less than meters per second.
Yeah, it's a little bit funky. So what I didn't do was take the step. Kilograms times meter per second squared would give you newtons.
Okay, perfect. Thank you.
Yeah, I apologize for sometimes I skip that step a little bit, but part of the reason that we had you go through all of the problems you have on the homework for doing the dimensional homogeneity part is to make sure that you're checking your dimensions as you go. So good question. Anyone else? Okay, terrific. All right, let's jump back to surface tension. And I had another problem set up for this, but let's go through we didn't quite finish the slides that I had for this segment or this part of the materials on Tuesday. So let's try to go through those and see if we can kind of figure out where to go here. And in particular, we will do a little breakout room session and see how that goes. And then I also will have a clicker question here at the end. All right, so we said that surface tension results from an imbalance of molecular forces at a liquid-free surface, and that causes it to behave as if it were a skin stretched over the surface. And the skin, we can say, is the result of these molecules from the liquid having to interact with each other and not having more liquid molecules above them, right? We have gas molecules up here. So we can still have liquid water here and gaseous water above, but essentially there's a lot more interaction with other molecules below this interface, and at the interface, these molecules, the liquid molecules, all kind of bond to each other a little more because they don't have anybody above them that they can bond to, all right? And so the water strider here on the right, I feel like that looks like a, what is the spider with the violin on the back that's really deadly? Not a black widow. Yeah, I know. That's what it reminds me of. I don't know. I'm not sure where I got this picture, but anyway. Recluse.
A brown recluse.
Brown recluse. Thank you. Yes. I grew up for about 10 years in Texas, and as soon as I learned about those, I'm like, yeah, I'm not going to go just rustling around in the shed anymore and find one of these. Okay, so on the right, we see this is probably more like a spider than a water strider. Water striders don't usually have, I can't quite tell if the body's in contact. It kind of looks like it is in this case. But a water strider will generally have 6 legs that are just in contact with the water. And because of surface tension, they are able to essentially support themselves on that water, and that's one of the problems you have in your homework. Okay, so let's go through this video one more time. Now, the water strider is neat, but we can also do this with these interesting little razor blades. So this is a very light razor blade. It's double-sided, and it's of course made of metal, and you can see that it floats well on the water simply because of surface tension. Surface tension is holding it up. Here's a heavier one, single-sided. That other side has a guard on it, which makes it heavier, and it sinks right away. And so the ability of surface tension to hold anything in place, particularly between these two types of razor blades, is kind of right on the cusp, right? It holds one, not the other. So their weight difference is in the realm of what surface tension can handle in this case. All right, so let's talk a little more. I forgot I have to do this stuff. Okay. Now, we talked about briefly, surface tension is this intensity of molecular attraction causing a membrane. We generally symbolize it as a sigma, a small lowercase sigma, Greek letter, and then it has dimensions of force per length. And that force per length means that it's only acting where it's in contact with something, right? The water strider, for example. When one of those legs is in contact, I guess the foot is at the end of the leg, when one of those 6 feet of the water strider is in contact with the water, it has some length to it, right? I mean, it's small, but it also turns out that the weight of the water strider is pretty small to begin with, right? So the question I think that you have to answer in your homework is what's the total length of these legs that work out to support a water strider of a given weight? Right, and so you look up the value of surface tension. Again, those tables that are kind of on the inside cover of that book I scanned, or you should now be able to find them more easily through the Wiley resources through Canvas. You can look up a value of surface tension for a given liquid type or fluid type at a given temperature, and be able to pull that into your calculations. Right. So conceptually, we can think about this as the force that's required to cut into that membrane. And we also note that there is a contact angle that is incorporated here. Now, the contact angle I'm showing here is maybe a little bit different than the one that we talked about with the example that I wanted to spend just a little more time going through. So on the next slide, I felt like we kind of rushed through this on Tuesday. So I want to go back to this and just talk it through again. So we take a small diameter tube, we put it into this pink fluid, and that small diameter tube allows for the rise of fluid inside the tube, all right? So it rises some height h, and we expect that, again, we have a hydrostatic situation. And therefore, if we were to draw, and we will in just a moment, a force body diagram for this situation, that there is some force that is pulling water up, holding it up, and of course there is gravity acting to pull it down. So surface tension in this case is offsetting or acting in the opposite direction as gravity, and it can only go so far, right? when we provide or look at the surface tension for water, let's say, we said it's in force per length. And what that means then is in the case of the tube, which all we're seeing is the cross section of these gray walls of the tube, parallel walls, but the entire circumference of the inside of this tube is in contact with the water. And therefore, if we want to figure out the force that is related to the surface tension, we take the surface tension and multiply it by a length. So in the case of a tube, we multiply that by the circumference of the tube. So what is the radius of the tube? We can say pi, what is it? 2 pi r, right, is the radius equation for a circle. As long as we know the radius of this tube, we can figure out what that surface tension force is that we call capillary rise. So capillary rise, capillary tube is a very small, fine tube. It comes from thinking about the capillaries that we have in our body, very small vessels that are moving blood around and so forth. A capillary tube then is a very small diameter tube that we can think about having this rise occur within. Okay, so what does the force balance look like? It's, again, it's got some height h to it of water or fluid that has been pulled up. There is some total weight force acting in the downward direction. Now, let's break this apart for a second. Pi times r squared is going to be the area of the inside of the tube, right? And then we multiply that by h, where basically these last three terms are just describing the volume of this tube. We multiply, the volume of the water that's being pulled up in the tube. And then we multiply by the specific weight. Remember, specific weight is gravitational force, the weight divided by the volume. And so when we have volume, this pi r squared h gives us the volume multiplied by the specific weight, then we just get the weight. So that should be a force acting in the downward direction. The upward force here is sigma, our surface tension, multiplied by the circumference of the tube on the inside, 2 pi r. All right? So that's how those come together. We can, I'm not sure why that happened. We can then basically put them together in the context of saying that they have to oppose each other, so they have the same magnitude acting in opposite directions. And we can actually solve for h. H is equal to, we can just basically take this equation and solve for the height that will occur within the tube based on radius, based on the theta will actually be somewhat fixed for each given type of fluid and its temperature. But let's say that we can plug that in at sort of a typical theta. Of course, gamma is in here as the specific weight as well. Okay. All right. So before I put you guys into a breakout room, let me first just say, let's just watch this video. So what I want you to do is note the question and pay attention to this video, then take that with you, because I realize that when I put you into the breakout room, you won't be able to see this anymore. So in the video to the right, you will see 4 tubes. You can see the 4 of them here. They're going to be inserted into this. I said it was water. Might not be water. It might be some other fluid, some liquid. Surface tension will cause the water or fluid, the liquid to rise up in each of the tubes. Why does water rise to different heights in each tube? And what do we know about the tubes based on this rise? Okay, so let's watch the video and check on the left and right. You can see these relative heights, right? You could actually measure. So there we go. We see this one rises to what? Maybe 0.7 inches or centimeters. This one's close, maybe 0.9. Oh, okay. Those are different than the numbers I get. Let's watch that one more time. So we're going to dip them in at the same time, and we're going to look at how much they rise. Okay, so here I can pause it after they pull these up. We get... Okay, so the final positions then are 0.6. Oh, I guess maybe we're off a little bit. Anyway, 0.43, 0.3 and 0.15 millimeters. That doesn't seem right at all. We're above 2 centimeters over here, so maybe more of those. But anyway, these are the final positions. Okay, so the question that you guys need to answer then, why does water rise to each of the different heights in the tube, and what do we know about the tubes based on the rise in each? All right, so I'm going to put you for 3 minutes into where are we?
I don't know why.
I can reclaim host as it turns out.
Yeah, do it. And then Alexi made me host because he's going to check the office hours.
Okay.
It makes me host automatically when I come in, so.
Well,
I might not be logged into like my account or something. I feel like it's something on my.
okay.
The automatic group making is so much better. Like last semester, we had people that we didn't want to put in groups because they hadn't finished this homework. So I was setting up them manually with like 60 students.
Oh, geez.
So, and I had like checking, and it was a lot. It's so like the automatic button is so nice. Although
After class, I will put the two like paper problems together and make them. I'll identify in the in the instructions that they need to submit. They'll have an online submission for each one, but they can be the same document, but we just need to make sure that the right answer is in each of the submissions. So.
Nice.
Okay, let me give them a 60-second.
I assume they've figured it out because the answer is a little bit.
If I close all rooms, I think they get their 60 seconds.
We'll see.
All right.
They might just all pop up all of a sudden.
Yeah.
It'll be scary.
That once happened. I was sending them to the group, and then they went and they came back, and it was like super scary. I don't know. I don't know if you remember that. It was like they all came back to class. They were like, "We didn't get into our group."
How is office hours for you guys?
I had a lot of students. Well, I mean, 5 or 6, but they kind of stuck around. And
Yeah, same. I like 4, but I asked a few questions.
I guess I missed mine on Monday, so I haven't.
Oh, okay. Yeah.
Okay, breakout rooms will close, and then it's got to count down for 60 seconds. So actually, while we're doing that, okay, we're slowly filtering back. All right. Okay, so does someone, Sarah, it could be you if you want, does somebody want to explain what they talked about in their group and just tell us what the different heights of rise correspond to?
Other than what was kind of like given away by that little hint on the video, we kind of talked about like why that would happen. And it was because once you isolate an equation for height, you're dividing by the radius. So consequently, with a larger radius, you would not rise as much. And with a lower radius, you would be dividing by less, meaning your level would rise more.
Yeah, good point. So oops. Oops. Oh, rats. Oh, I'm not in presentation mode. Sorry. Right. So this equation right here, you're right. If we, okay. I don't know why I can't. I was just hide you guys. Okay. Right. H here, if you isolate that, is going to be inversely proportional to R, the radius. So great. All right. So now let's move forward to, to a poll question here. So go ahead and get your clickers out. Let me start class for the day. Okay, and I'll start the polling in just a second. It'll be a 60-second countdown. So you've got nice cool tap water with a temperature of 12 degrees C. You find that you can readily float a paperclip on the water surface due to its surface tension. If you attempted to do this with water that was 75 degrees C, so we warm up the water, do you think you'd be more or less likely to be able to float the paperclip? So just think it through for a minute. I'll get the poll going. And let's see. Here we go. We'll let that go. So 60 seconds. Think about it for a little bit and then go ahead and vote. more or less?
They want to sanction Governor Cuomo? Why? Triple up his emergency powers.
So think through it a little bit. Remember we talked about those
That's crazy, right?
molecules interacting with each other at the surface versus at depth. What does that mean when we warm them up? Are they more likely to hold or less likely to hold? Before I do this, let me just check. Where is my? I wanted to see it. Surface tension. No, I don't have. Yeah, I thought we had a table for these, a nice plot. Okay, so what do we get? All right, so the poll has ended. We had 82 and 11 makes 93 folks responded, and here's the results. Oh, come on. Go ahead and show them. All right, here's the results. 88 or 82 of you, 88%, said B, less likely, and 11 of you said more. And those who are in the majority are correct in this case. You are less likely to be able to hold up that paperclip if you increase the temperature of the water in this case, whichever fluid. You basically reduce surface tension when you increase temperature. And the reason for that is simply that when you heat up your fluid, you have a lot more energy involved, and you're going to have a bit more movement, and therefore you end up with just a little less of a tight bond there to make it work. All right, let's see. A couple of you, looks like it didn't pop up. You won't see you should have seen the opportunity to just put in a letter. So I'll keep the chat. If you didn't see it, let me know, or let me know in the chat, and just make sure that you are connected to the correct class. And I'll just make sure that we include you guys for the participation today.
Mike?
Yep.
Is that temperature relationship purely conceptual, or is there an equation that could justify that?
There probably is an equation. I don't think we have it in our book, and I think it's probably going to vary based on the molecular interactions. And so I don't know if it's a real simple. There probably is a general one, but I guess I'm not sure if it would come down to trying to think of what the variables would be in it. But there might be a specific one for each fluid. So probably up as a curve, right?
Right. So generally, it's just that the molecules of something that's colder are closer together than something that's warmer.
Yeah, they just don't move as much, and so they're a little
Okay.
more tightly bonded to each other. Yep.
Okay. Thanks.
You bet. Okay, let's see. All right, so we're getting close to the end of time here. So the wrap up for today, I guess we're done a few minutes early. Homework